Okay, good morning. As Daniel said, my name's Hugh Carson. I'm a senior applied scientist within the AWS Center for Quantum Computing, and I'm going to be talking to you today about PALACE, which from this backronym you can see stands for Parallel Large-Scale Computational Electromagnetics. Okay, firstly, why make PALACE? The Center for Quantum Computing is aiming to create a fault-tolerant quantum computer able to perform industrially relevant calculations. To this end, the CQC is employing a technology called superconducting qubits. In an enormous simplification, these devices consist of a slab of extremely pure dielectric with a very thin layer of superconductor deposited on top, with various patterns cut into the surface to achieve capacitors, inductors, waveguides, things like that. By varying the shape of these cutouts in the surface, different circuit parameters can be achieved. And with different circuit parameters, different quantum bits or qubits can be achieved. There are many complicated quantum mechanical effects important in the design of these components, but for the purposes of this talk, the most important thing is that the majority of the physics associated with the design isn't actually quantum in nature. It's classical electromagnetism governed by Maxwell's equations that you see here on the left. So to analyze the performance of such a chip, a designer needs to understand the full electromagnetic fields and how they vary in space and time. Okay, so onto the example you see here on the right. This is a cut-through visualization of the top surface of a prototype device. And so what you're seeing here isn't actually the top surface. This is a cut coincident with the surface of the metal. And the colored regions you can see is the seam between where the metal is cut away and where the metal existed. So you're sort of seeing the outside border of the chip shape. And the full simulation is 3D with the chip enclosed in a cavity. But I'm only showing a 2D visualization here because the rest of it's not quite so interesting. The color here is from the electric field magnitude. So red is, I think, about 10 to the minus 10 to the 3, and blue is about 10 to the minus 3, I think. Yeah. And this is the first eigenmode of the circuit, which you can see is basically concentrated in the top left. But if you look a bit more closely, you can basically immediately see one of the problems with this. That field isn't just concentrated in the top left, though most of it's in the top left. You're getting various interactions with the top right, these very sort of squiggly structures, which are resonators. And this kind of comes from the elliptic nature of the equations that we're solving here. This is in frequency domain. And for designers, it's pretty important to be able to investigate these sort of long distance effects. And so what that means is you need to be able to simulate relatively large devices with relatively complicated surface patternings. And so what this basically means is that for us, given all these considerations, the CQC saw a future where we would need to be able to do very large EM simulations. And we decided that the existing tools wouldn't scale to our goals. Additionally, we saw the opportunity to take advantage of the significant improvements in HPC algorithms coming out of the national laboratories and other open source organizations, such as MFEM, along with the growth in cloud computing capabilities. So it's something in AWS we're quite aware of. So from this idea, PALACE was born with the aim of leveraging modern open source scientific software computing to perform full wave 3D electromagnetic simulations in the frequency and time domain. So the project was started by Sebastian Grimberg. You can see is the picture of the top person in the top right here. But the project has grown now, and most of the contributors that we have at this point are shown here. And along with, as the number of human contributors has grown, actually the number of open source projects that we're leveraging has been growing over time. And you can see some of them here on the right. All of these are important, but some are particularly worth calling out for the audience here. And those are MFEM, which you can see front and center there, but also particularly libCEED in the top right and Hyper just below that, which are all made very they're all very heavily used throughout the Palace code base. And you can also see sneaking in on the right there, the SPAC symbol, because we're increasingly starting to use SPAC for a very sort of elegantly packaged user experience, if not developer experience. So in 2023, Palace was released open source on GitHub, and the repo is given here in the bottom right. You can either follow that URL or that QR code will take you to it. And we've found this tremendously useful within this UGC for our electromagnetic simulation needs, and hope to contribute back to the open source movement with it, both through it and through our upstream contributions to various packages like MFEM, libCEED, and such. So if you're interested in giving it a go, we have some documentation, we have examples for the various solvers, and we have recently actually added a quick start guide, which will hopefully provide a approachable way into the Palace codebase. Okay, onto the physics. So Palace is made up of 5 core solvers, the first 2 of which are the static solvers, so electrostatics and magnetostatics. As the name suggests, these are classified as solutions to Maxwell's equations with no time derivative. The first is no moving charge, electrostatics, and the second is charges moving at constant velocity, so magnetostatics or direct current. The electrostatic solver solves a weighted Poisson's equation for the scalar electrostatic potential phi using H1 finite elements, from which we can compute an electric field as the gradient, and we can also compute capacitance matrices between various terminals in the circuit. This picture is actually taken from our 2 spheres example, which is slightly contrived, but allows you to compute the capacitance between 2 matrices and shows how you would run 2 simulations, one where you charge each of the spheres in turn to unit, and the other one is held at ground. The other solver that here, the magnetostatic simulation solves a weighted curl-curl system for the magnetic vector potential A using Nedelec finite elements. And from this, we can then compute the magnetic field density B, which is the curl of A. And the sources that drive this are defined using current loops. So for the electrostatic simulations, we're making use of PCG and algebraic multigrid. And for the magnetostatic simulations, we're making heavy use of the AMS solver from Hyper. So both of these are workhorse simulations in circuit design, with the systems being solved once per terminal in a given design, and then multiple simulations being done per design as parameters are sort of varied. So a given design might have to sort of order tens of terminals. So you can see we're pretty quickly going to be making a very significant number of these solves. And so wasted time here can pretty quickly add up for us. The next 2 solvers in Palace are the driven and transient simulation types, the former being in the frequency domain and the latter being in the time domain. The PDE formulations for each are given here. The details aren't especially important, but both are discretized using higher order Nedelec elements. And Palace makes significant use of Nedelec finite elements. So for many of you, probably your only interaction with Palace thus far has been Sebastian or I submitting PRs for various tweaks or fixes to Nedelec related AMR things. But we have been trying to upstream these efforts into MFEM where we can, so hopefully helping out the community. The driven simulation can be run in uniform mode, where the system is directly solved a selection of frequencies, and the output functions of computers such as scattering matrices. And it can also be run in adaptive mode, where we use a projection-based reduced order model to develop a fast online evaluation process, which allows us to then rapidly evaluate over a large range of frequencies. These projected values are typically sort of less than 0.1% loss compared to the full fidelity, but thousands of times faster. So it can really open up doing frequency sweeps, which is quite important for the kind of work that we're doing. And so these bullet points here are the various features we support. So we support anisotropic and lossy material properties, absorbing boundary conditions, scattering parameter calculations, lumped and numeric wave ports. And the orange text here is actually sort of relatively recent features. So we now support periodic and Fouquet boundary conditions. So those are sort of periodic structures with a with a phase shift. And we also now support non-conformal AMR with numeric wave ports. This is the non-conformal submesh capability recent. And we also support adaptive time stepping in the transient simulation through sundials. The final solver making at Pallas is the eigenmode solver, which we make heavy use of in computing resonant modes. And so, like the ones we saw earlier on the chip surface, the eigensolver can be easily the most computationally taxing thing done within Pallas, because it basically consists of repeatedly solving a linear system. So we can pretty quickly rack up a lot of time in our linear solver using this. And so the formulation is built around this second order system decomposition that you see in the top right, and we solve it using SLEPC or ARPAC. As with the previous two solvers, we support anisotropic and lossy materials, absorbing boundary conditions and lump ports, and newly supported periodic and Flaquet boundary conditions. Something which is just around the corner for us is actually a new nonlinear eigenmode simulation. So this will allow us to support both numeric wave ports, where you actually have to solve an eigenmode problem on the boundary of the domain, but also second order absorbing boundary conditions. And there's a world where we might start to support nonlinear material properties. We personally don't need this internally, but this is the kind of thing which this capability unlocks as and when someone might need it. So I just want to call out one thing here, which I've spoken to a few people about. A particularly difficult aspect of this sort of frequency domain simulation basically comes from that negative sign in front of the omega squared, which is making the system technically indefinite. And so our solver strategy mostly seems to consist of P multigrid, because a lot of our work is in sort of microwave engineering, so it's not too bad, and we can kind of get away with a P multigrid. But one thing that we found is that to get reasonable performance, we're having to use a sparse direct solver as the course step. And for that chip that I showed earlier, which I'm going to show here again, that can pretty quickly start to become the actual limiting factor. So we can request a few hundred nodes relatively quickly. So we're talking, of the order of 6,500 cores, MPI jobs. Typically, we're using CPUs rather than GPUs just because of availability. Like I can request 100 nodes of CPUs and basically get them in less than 5 minutes. GPUs, you might have to wait a while because they're very popular. So there's a bit of a trade-off there. But this simulation, so what I'm showing here on the left is the mesh, actually the surface mesh that was used in the simulation. In the middle is a full representation of the electric field, and the right is that cutaway view that I was showing previously. So the mesh that is generated here is actually from another recently open source project from the CQC, which is devicelayout.jl. So this is a Julia package. The CQC makes heavy use of the Julia language. And we use this for doing schematic-based design, where we can formulate a graph of the overall chip design. And then one of the nice new capabilities within it is it integrates with Gmesh, and we can generate meshes like you see here on the left. So the problem with this is this particular mesh has about 1.5 million elements and 2.2 million edges, which for Nedelec degrees of freedom, that gives 2.2 million P1 Nedelec DOFs, which basically defines the size of your sparse direct solver, which means you are pretty quickly running into the limiting factors here for sparse direct solvers. If you pour in more MPI ranks to handle higher order, to divide that number down, you're actually making the sparse direct solver slower and slower and slower as you're over parallelizing it. So there's a bit of a trade-off between those two. And so just to put a bit more numbers to this, so this one has 2.2 million P1 Nedelec DOFs and 69 million P4 DOFs, and using 32 C7G.16x large, which is the sort of the compute grade Graviton 3 instance type, which we use very routinely, basically through a mixture of availability and cost efficiency. So this is an ARM chip, and we run it using the Elastic Fabric Adapter, which is what EFA is, and OpenMPI. And I said this was fourth order basis functions, but solving this linear system to a tolerance of, I think it was 10 to the minus 6 for the eigensolver, and a linear system of 10 to the minus 7 required solving 198 linear systems and 16,384 linear solve iterations. That's about 83 iterations per solve, which is pretty good, but that's still pretty prohibitive for running these things. So this is a turnaround of just under 6 hours, which is fine as a sort of, we don't routinely do a whole chip simulation, but a designer would like to be able to trigger like 10 of these as they go home for the night and come in the morning to the full set of results. We'd like that to be faster, and that's one thing we're sort of really pushing on here. But as you can probably see from the mesh here on the left, we're starting to push the limits of what these meshes can reasonably do, because you can see there's a lot of concentration around the features and it coarsens pretty rapidly. And the effect of this is that the kappa that we report from the like parallel mesh stats, which MFEM reports, is about 1,000. And Ned-like elements appear to have very poor conditioning as kappa starts to grow. So we're in a sort of a trade-off here where if we don't make kappa large, we have too many elements. If we make kappa large, the system's hard to solve anyway. And so we're kind of between a rock and a hard place here. Another thing which is we kind of want to look at in future is that if you look at these electric fields, you can kind of see that along the paths, as you see in the top right, there's actually not that much variation. You know, these are sort of like quarter wavelength, half wavelength structures. So it's very smoothly varying in that direction. And then if you look perpendicular to the path, there's a very rapid gradation. And so immediately you start thinking anisotropic meshes. Like the physics is basically deeply anisotropic around these structures. But as I said, that's not very good from a linear solver perspective. So we're back into this rock and hard place. So if anyone has ideas on solving these coarse systems very well, or even just general preconditioning, I'm all ears. Socrates and I have already been discussing this. Okay, so that was from the top style simulations that we're doing. The other type of simulation that we often do is sort of, you can think of as a bottom up. This is a single transmon case. People who've been following the Alice release will probably recognize this structure at this point. But this is basically one of the sort of smallest kind of interesting structures that we might simulate. It consists of a single transmon, which is sort of you can think of as a nonlinear inductor element, which makes up the sort of the core quantum piece of technology behind a lot of these devices. So it's that attached to a resonator. And basically, in this case, we can run the simulation pretty quick, and we can basically sort of demonstrate reasonable strong scaling here up to about, I think it's about 7,500 cores. So just to describe these figures you see here. So P6H1 means sixth order elements and one uniform refinement of the mesh. So this gives you, using a sort of a logarithmic P refinement, this gives you 5 steps in your multigrid hierarchy. And then P3H2 is third order elements and 2 uniform refinements. So this is sort of trading the higher order accuracy situation. And so the x-axis here is the number of MPI cores, and the y-axis of time on the left. You can basically see that for the P3 case, we can get down to sort of order 5-minute turnaround. And given it takes about 5 minutes to request about 100 nodes, this is basically of the order of the sort of overall designer experience. You can also see that the P6 solve is longer and still seems to actually achieve better strong scaling as you go on the right. So the strong scaling there is the time on, I think it's 1,280 cores divided by the time on the time for the number of cores on the x-axis. And so closer to 1-to-1, the better, basically. And we can, I think, using a similar standard to the rest of MFEM, consider 80% like a reasonable result there. Again, this is Graviton 3 instances, and yeah, those are the number of degrees of freedom. So some of you might be thinking immediately, why were you doing uniform refinement of the grid? And that's a very reasonable question. And these plots basically show you that you shouldn't. So there are kind of two ways to think about the cost of the simulation from our designer's perspective. They don't really give a damn about solution orders, mesh refinement levels, all these things. They care about time, accuracy, and compute costs. Compute cost is not too much of a problem for us, but is always something we try to keep in mind for more external users. And so these two plots are kind of the two different worldviews of looking at this. And so first, starting with the little crosses, the little crosses are the results from the previous plot with the uniform refinement levels and different numbers of cores. So you start from the palest cross is at 1,280 cores, and you're getting to more cores as the crosses get darker. So as you can see on the left, you use more cores, it runs faster. But then if we look on the right, which shows the core hours plot, you can basically see more evidence of the strong scaling here, where I can increase the number of cores, but the actual total cost in core hours doesn't really go up. Those crosses are pretty well clustered. The dark ones are slightly to the right, but really not very much. So that basically says if you want to go faster, you can just pour more compute on it and you'll get reasonable results without having to pay too much in inefficiency. But the solid lines here are using AMR. And so making a slightly arbitrary decision here, I start the AMR from 1,280 cores, so the same instances, the palest cross on these plots, and I just run for 2 iterations. The marking strategy here is actually Doerfler marking, so it's a bulk chasing method. So it works in parallel and it's targeting 70% of the mass of the error estimate. And the actual error estimate here, which is on the y-axis, is a normalized ZZ error estimator. And we slightly break with the dogma of the error estimation community here. And we actually are using a global solve to construct smoothed D and H fields. So you can think of that as like epsilon times E and mu inverse times B. And the reason we do that is because we are using partial assembly and libCEED, so it actually ends up being not that bad. Like we're paying quite a lot in terms of the extra storage space for the H and the D fields, which are in Ravi-Atomar and Nedelec spaces, but the actual solve doesn't end up being too bad on reasonably conditioned meshes. Again, this is something we'd like to look into a little bit more. But the big takeaway is if you just care about either time or core hours, turn on AMR and you'll get better results for less, shockingly enough. And so you can see that here, it's like this 0.1, sorry, the normalization here, we're dividing by the electric energy plus the magnetic energy because the units end up matching up correctly for that. As you can see that a 0.1 error estimate is a pretty good practical value that we've seen so far for designers to get like reasonable answers out of this for all of their actual output functionals. And so we can basically turn around the whole simulation sort of order 5 minutes with AMR using only the 20 nodes that we needed. Okay. And finally, I would be remiss being an MFEM conference to not present this because basically all of the performance that we achieve within Palace comes down basically to this diagram. This diagram plus libCEED is kind of the key. And so there's a lot of technical terms that are going on, but yeah, we use matrix VP multigrid, we use partial assembly for the higher order operators, and after that colon, the second line, that is a lot of work from 2023 through 2024, basically, particularly by Sebastian. So supporting that sort of mixed meshes, simplex elements, H1, H-curl, H-div, conformal spaces, scalar and matrix value coefficients, linear interpolators. There were a lot of surprising little holes in that sort of patchwork that had to be like you'd sort of advance, find a little hole, patch it, and keep moving on. So hopefully that is something that we can say that we've managed to help the community with a little bit. Okay, going to wrap up in a moment, but so one thing, Palace is an open source project. So most of the contributors thus far have actually been AWS CQC employees, but this is all happening in a public GitHub repo. If you're interested in electromagnetics, you can just join in. Like, there's no real barrier here, aside from the speed with which I can review PRs. So please, by all means, contribute if you're interested, or even just take it for a run and open an issue report for me, because I'll try and fix them. Okay, so just a little look to the future. So three things that we're currently sort of working on quite intensely, and these are on the verge of being merged. We have scattering far field extraction. So this is particularly for our antenna design. So this is something which we don't really do so much within the CQC, but we're getting into a little bit. Nonlinear eigenmode calculation, I mentioned that. Flux terminals for magnetostatics. So it turns out if you're trying to make superconducting logic circuits, so not quantum ones, just like a normal transistor style one with superconducting logic, you need the ability to specify flux through specific loops and then calculate mutual inductances between them, which slightly entangles things and gets a bit more complicated. So there's actually a PR within MFEM to allow applying boundary conditions on topologically d-2 objects. So if you're in Nedelec space, you could like define a boundary condition on a wire within your domain, which is surprisingly fiddly in parallel. So yeah, in the future, we're looking for more improved GPU support, more and more work on the, oh yes, for AMR, one thing we'd really like to be doing is geometric multigrid. So once we do a refinement level, we'd like to keep the core solve, the original one, as the same size. Like we could just keep paying for that and just have an extra depth of this geometric multigrid. That requires having a transfer operator between those that works with the non-conformal structures. And then finally, as always, better coarse preconditioners. That is going to be the limiting factor for us over time. So we're always interested in more. Okay, with that, I'd like to say thank you. And this is supported, obviously, I couldn't put every single name on this slide, so I opted mainly for my manager who supports me in getting to work on this kind of stuff within an industrial setting and also get to open source it. So yeah, and this QR code takes us to the repository. This QR code in the bottom right will take you to the past repository. Okay.
Thank you. Very nice talk. I think I might have missed the point for the AMR. This is still the indefinite Maxwell they do AMR on?
Yes, actually, it's for all of the solver types.
And what is an indicator there? What is the error estimator that is used there?
The error estimator, so we take the E field and we multiply that by epsilon, then we smooth it onto an RT space. So we smooth the sort of numerical D field onto the appropriate space, and we do the same for the numerical H field onto an appropriate space, and then we measure the difference between that and the...
and this seems to be working well? It
works surprisingly well. There is a definite theoretical hole in this, in that if you put constant fields for those two, it'll return a 0 despite being a terrible answer. So technically, there is a missing residual portion of this.
Right.
And as someone with an error estimation background, that does offend me quite deeply, but it's a bit difficult to do a curl strong form operator within the sort of MFEM paradigm. So that is something we would like to do. We just haven't done it.
Okay, thanks.
No worries.
Okay.
Victor. Hey, so you showed some unstructured meshes and you mentioned GPUs. So I was just wondering, are you, when you do the GPU runs, are you also doing it on mixed meshes or TET meshes? And
yeah, we support GPU for mixed meshes, TET meshes, hex meshes, strictly 3D. But yeah, we support it for all of our mesh types. This is all done using libCEED in particular. So we're really leaning on them for a lot of that capability.
Okay, other questions?
I'm curious about your software stack. On an early slide, you had a bunch of logos for a bunch of different packages, and running all this on ARM Graviton, is it all seamless and perfect, or is there a lot of difficulties with
that? It is definitely not seamless and perfect. So we maintain a super build system. So we basically build all of these from source ourselves outside of the SPAC environment. And I'd say about half of those, we have a patch to the build system that we're maintaining internally. Most of these patches, aside from the MFEM ones, consist of just ripping out a lot of stuff, which tends to be debris that doesn't necessarily work with a lot of things. But like to give you an example, I actually don't, they're not on there, but like we have mumps. Mumps the other day decided to no longer support external ScalePack, Metis, and Parmetis. So they're now using Git submodules. No idea why, but they're now sort of like keeping these all reconciled with each other within that process is tricky, but being able to build everything from source ourselves basically allays a lot of that problem.